Okay, everyone, how's everything? Project started?
Yes.
Going well?
Progress.
In progress. Very good. Okay, today I'm going to talk about slightly different things about the significance of dynamics for lateral load analysis. This is the same presentation that I made last week in Cebu, in Philippines. And this is for, and I thought that this is quite, a lot of people ask many questions, and they thought it's very important and interesting and something like that. So I think our class should also learn the same thing, because you're also graduates already, right? So that seminar is for, I'm not so sure if I have shown any of these slides before, because I keep forgetting where I showed what. So many times this is presented, but please tell me if you've already seen something, okay? Did we talk about this? Not yet. Okay, good. Now, we are talking about lateral load response and lateral load systems, and one of the most important part of the lateral load, different from gravity load, is dynamics. For gravity load, normally we consider static effect of the loads only. That means we expect the dead load and live load to be applied slowly, and we do not expect the structure to respond dynamically unless we are dancing on the floor, right? In that case, the floor might vibrate and it might give you dynamic effects, and sometimes that is also important. Sometimes the bridges are important for live load dynamics due to the vehicles, due to even people walking on it. You might have heard an old statement that if the army, when the army is crossing a bridge, they ask them not to walk in step, to break the step, right? And there's a reason for that. Structural engineering is behind that. So we will talk about these dynamics today. Both, I know you're studying dynamics with Professor Penning, so many of the concepts you already know, but today I want to talk about how it affects the lateral response of the buildings, right? So, doctors, you're too young to go to the doctor, and I hope you don't have to go to the doctor. But if you go to a hospital and you go to see a doctor, the first thing they all want you to do is go to a nursing station and ask you to take your blood pressure and your pulse, right? And then after that, a good doctor can always tell whether your human body is healthy or not healthy, right? Something wrong with you or not something wrong with you, and then they will say, okay, do this test. But the first thing is blood pressure and heartbeat, most important. And all these trackers that people wear these days, and smartphones and Apple Watch, they all track your heartbeat. And that from the heartbeat data, they can tell you when you're doing well, you're exercising well, your health is good, and that the heartbeat should be in a certain range. What's a good range? How many heartbeats per minute?
80.
70 to 80, right? So we know all these things. So same thing is with structures. Structures also have a heartbeat. And if we know how to look at that heartbeat, and we know what is a good heartbeat and how to manage that, then we can understand the dynamics of the structures and also the behavior of the structure. So heartbeat and blood pressure, both are very important. So we know when you go for that, when you run, you're always tracking over time how your heart is performing over time. So it's like a time history of your heart performance. So all of that is actually very relevant to structures also. Last time we started the discussion with the tiger. Today we are starting the discussion with the doctors. So there is a blog video on this one. You can find it under my name somewhere on this issue. I don't know if it's working. Yeah. So are we listening to the heartbeat of structures? Please look for this one. I don't want to show you. You can find on the internet. It is somewhere, and then you can listen to this. You don't need to, you can listen to that. But what I'm saying in that video is what we are discussing today. That means the dynamic response of the structures, and which is the heartbeat of the structure, especially for earthquake and wind response that we are talking about so far. So you already know what the system is, you have studied, right? Okay. These equations, everybody knows. Newton's, right? First law, everybody knows. So Newton was, long time ago, he already knows that force and mass and acceleration are related. So if there's an acceleration and there's a mass, there's going to be force. But the assumption by Newton is that the body is rigid and has no damping, cannot deform, it's a rigid body. So whatever force you apply, it goes to accelerating the body proportional to the mass. Or if the body has an acceleration and a mass, the force applied required to stop it is directly related to these two quantities. But in our case, we are talking about structures. Structures also deform, and they also have energy dissipation. They also dissipate energy when you try to change their state. So those two components are missing in this equation. And structural linear's view of the dynamics is this. You already know that. So there are three components to the force. So there's a force that you want to apply. It will be taken up by three components in the body. One part will be taken up by stiffness and displacement. One part by velocity and damping, and one part by acceleration and mass. So acceleration and mass, Newton's part is here. These two parts we added into the equation to handle deformable bodies that also dissipate energy or absorb energy, right? So that is the, but this is still for linear elastic deformable bodies. It is still not for a real structure, because real structures are more than this one. We are still missing one more term that we will talk about. We have talked about a little bit in the last course, and I want to bring that discussion to connect today to this discussion. So this is the stiffness part, and last time we talked a lot about stiffness. So you've seen this one, right? Yes. Last time we showed that. So dynamic response is a sum of the response from the modal response. We talked about the importance of modes already, right? Yes, okay. So we know that. So now we are talking about, we already talked about this equation also, that when you apply, so we can consider the structure to be a big spring. So if we consider the structure to be a big spring, then stiffness is here, and we only may have equation. So for static structures, we only have this equation. And for Newton, we have another equation, mass and acceleration equal to force. For our structures, if we ignore dynamics, our equation becomes simple like that. But when we have dynamics, we have the full equation over there. And we talked about the structure stiffness matrix last time. I just want to remind you in the last time that stiffness is coming from many components: material stiffness, section stiffness, member stiffness, structure stiffness. So cross-section geometry comes in, material response comes in, member geometry comes in, and structure geometry comes in to making up the stiffness. And each of this has a linear part and a nonlinear part, because these are not linear only as we are assuming so far. So each one of them can be, material can be linear, nonlinear, cross-section can be linear, nonlinear, members can become linear, nonlinear, structure can be linear, nonlinear. I'm going to stop here, and I'm going to ask you each one to give me an example of a material which has nonlinearity. Material nonlinearity. Which material is nonlinear?
Rubber.
Actually not. Rubber is quite elastic and linear. Yes. Which material is nonlinear?
Concrete.
You missed it already. Concrete, okay. Which cross-section, when I say cross-section nonlinear, what does it mean cross-section nonlinear? What does it mean cross-section nonlinear? Skip. What does it mean cross-section nonlinear? Give me an example of nonlinear cross-section. Skip. Skip. Cross-section, not material. And we already said rubber is linear. Were you not listening? Nonlinear cross-section. Skip. RC, reinforced concrete, because it's cracking when you load it. The section properties are changing. You people don't remember I spent so much time on these properties of crack cross-section and all of that. Reinforced concrete is a nonlinear cross-section. Reinforced column or reinforced section or a slab or beam. Nonlinear member. How do you define a nonlinear member? What is member nonlinearity? We talked about it a lot. Okay, skip. Next one. I don't have the whole day for you. Okay.
Maybe member that already yield.
Member that already yield. Not really, because it's a starting case. Okay, little bit, I would say 50-50. Next one, still, nonlinear member. What does it mean, nonlinear member? Nonlinear member. Nonlinear member. No, that is correct cross-section nonlinearity. Nonlinear member.
Any component.
Beam with a hinge, no.
Buckling and
Buckling and P delta. Simple. Buckling and P delta is the most, we talked about this column, column slender, as I explained to you, this is the cross-section nonlinearity, this is material nonlinearity, buckling and P delta is the member nonlinearity. Structure nonlinearity.
RC structure.
Now give me a real example where structure becomes nonlinear. Okay, last one. Steel structures, everything becomes nonlinear because it's a sum of all of that, but I'm talking about a structure becomes nonlinear because some members become ineffective in some load cases and some members become effective in some load cases. For example, if you have yielding of the cross sections or buckling of a member, some members will become ineffective in the structure. So structure, if originally the most common example is the frame with diagonal two bracing wires. So that if you push it in one direction, one member will be in compression, second one will be in tension and compression. Compression member will simply become ineffective because wire cannot take compression. But if you go the other way, one wire will take the tension, other will take no forces. So this kind of thing. So please open up your mind. I'm quite surprised that basic, simple questions most of you could not answer today. Then you say our grades are not good in exams. You cannot complain. This thing we have studied so much, and very basic, simple things for engineers to determine that. Anyway, this is the example of nonlinearity. I've already shown you last class, right, in the book also. So linear elastic. I don't want to ask the question again. Give me an example because we did that last time. Linear elastic, linear inelastic, nonlinear elastic, and nonlinear inelastic material. Which is concrete? Concrete.
Non-linear inelastic.
Okay. You had a good chance. The second one. Dynamic equilibrium. So we talked about the dynamic. So this is the total equation of structural equilibrium. I think I've shown this before. So now we have a complete equation, nonlinearity coming into the equation. So the total equation is now external force. If you apply external force, it is now taken up by 4 components, not 1. Newton thought only 1. Linear structures think also only 1. The linear dynamics thinks 3, but total structure is 4 components. So external force taken up by mass acceleration according to Newton, and taken up by damping and velocity according to energy dissipation, and stiffness and displacement because of the structure is displacing, and nonlinearity. That means it is becoming nonlinear. Some force is being lost in nonlinearity. So you might be questioning, how this nonlinearity is a force correction. Please, again, I'm sure you also forgot if I show you this slide, so it doesn't matter. But if I showed you, then this nonlinearity is also composed of complete linear equations. So it is nonlinear because this nonlinearity itself depends on all of that. So there is an equation inside the equation, and there's another equation inside the equation. That's why it becomes nonlinear, right? So nonlinearity is a iterative. You cannot solve this equation, even if you want to, because the equation's answer is inside the equation itself. So that's why nonlinear problems cannot be solved directly. How do you solve nonlinear problems? Iteration, hit and trial, finding the solution in the dark. So that is the correction, nonlinearity correction. So if this is the linear behavior according to stiffness and mass, and if you put nonlinearity, you will get the red line. So the difference between linear and nonlinear response is the nonlinear correction factor, right? So if there's a nonlinear response and there's a linear response, the difference between linear and nonlinear force will be the nonlinear component making that change. So it seems quite simple that we can find the difference between linear and nonlinear, and we can find the nonlinear component, right? But what's the problem? what is the problem in this approach? People, the red line does not exist. We don't know the red line. We don't know the nonlinear response. We only know the linear response. Because I just told you, nonlinear response cannot be determined. So the red line is not known where it is. If we know the red line, there won't be any problem. But we don't know where the red line is. We only know the linear line. So then how can we find the difference between a line which does not even exist yet? That's where the iteration comes. We try to start from here and we try to keep close and keep finding that red line and try to extrapolate a little bit and then step by step, close, small. We try to keep two lines in focus. So we don't try to find this line in this way. We apply a little bit load, and if it is away from linear, then we find that nonlinear correction factor by iteration, by a small margin. Then we put that point. Next time, take the previous point. Then there is many techniques used to try to find this red line. And please remember, sometimes we can never find the red line. That's why sometimes the nonlinear analysis takes 1 week or 2 weeks on a very fast computer, and in the end says, I'm sorry, I didn't find the red line. It does not converge, does not give you the nonlinear response. So it has happened to us in some projects. After running the program for 27 days, we could not find the red line, or we could not converge in that project because the nonlinearity is so complex that the program could not find it. So many nonlinearities or something like that. Sometimes, funny thing is that completely linear structure also do not converge because there is no nonlinearity. So the program is trying to find a red line, but actually red line and the blue line are the same. So it also fails. So it's not easy to determine the nonlinear response. That's why it is so complicated, so difficult, so time consuming. And that is your main job, to learn how to find nonlinear response. This is one example where this nonlinear response is found by the program, and you can see it going up and up a little bit, and also calculating where the damage is. So that's the nonlinearity at each location, more, less. So as we go along, the nonlinearity is spreading, the damage is spreading, and the program is able to trace that nonlinearity step by step, and that's where it is. So you can see now this is the structure deformation, load, and nonlinearity are being calculated step by step. So step number 50, so it took the program 50 steps in this case just to find that nonlinear curve. At each point it is iterating and finding that, and corresponding damage state. So these different colors show how much damage has occurred or cracking has occurred in each of those components in the structure for this damage, how much cracking, how much yielding is occurring, and the structure is becoming nonlinear. This is the most common thing you people will be doing in your thesis and in our office. So we always try to find the nonlinear response of the structures to lateral loads. So this is lateral load. We push the structure, and then we say, oh, let's find out the nonlinear response. That's why if it's linear, it will go forever. But here we can see that it starts to deform and then become very flat. Stiffness becomes 0, and then we stop. And after some time, actually it will go down and fail. So that is the job of, so for earthquake, we always expect the structure to become nonlinear, and we need to find this nonlinear response either by estimation or by real analysis. Almost all theses done with me and Professor Penning generally are doing this and using a program called Perform 3D, which is the one, this program, right? Not ETABS, not SAP. So, and we are performance-based design, all depends on this one. So we'll talk about that again. So just to give you an idea, lateral response becomes nonlinear, especially earthquake. Even large winds can make the structure nonlinear. So coming back to the big dynamic equation, where we have everything, this equation is a very nice equation which has every response built into it. So if you are looking closely, you can find many things from this equation. For example, if you assume that damping is 0 and no external force, no nonlinearity, you get free vibration equation. You know what that is. You get natural frequencies, you get mode shapes, you get the natural period. So from there you can determine the free vibration of the structure. And I'm sure you have studied quite a bit about that. So we get natural frequencies and mode shapes, and these are critical for lateral response. Entire lateral response of the structure, no matter what type of structure it, depends on the natural frequencies and mode shapes, because the total response is the sum of the natural period, natural response. So if you want to determine response to wind or earthquake, you must know the modal response or the natural frequencies. So that is very critical. So modal analysis, please remind me, have we talked about this already? Okay, so this is the heartbeat that we were talking about. So if you are a structural engineer and you want to understand the structure, you must listen to the heartbeat of the structure. And that heartbeat is natural frequency. Just like our heart, tick, tick, tick. Whether we're sleeping, whether we are working, whatever we are doing, heart is beating. It never stops. When it stops, then that's the end. So as long as we are alive, it never stops. Same is the case with structures. Structures are always vibrating. They never stop to vibrate, whether there is a load or there is no load. They are always vibrating, because you have seen, without external load, without damping, without anything, they are always vibrating. The vibration we can measure. They are vibrating enough for us to measure that vibration. If you watch closely, tall buildings with a very clear eye, you can actually see the vibration by camera. If you capture the video high speed enough and detailed enough, you can actually see the tall buildings vibrating in natural modes. And then you can measure those vibrations. But measuring is one, calculating is another one. So we can do the calculation, we can do the measurement. Most important thing is that this is very important. Determines the inherent frequencies of vibration. Each natural frequency is related to a period and a shape. So each unique frequency, natural period, has a time to oscillate and a shape to oscillate. Both of this is critical for us to see how this is happening, because we are going to study that for all of the other response for the lateral loads. The time period is the time it takes to complete one cycle. The mode shape is the deformation pattern. Remember, mode shape is not real. Is not a real number. You need to relate it to some loading to find the real numbers. So mode shape is only giving you a relative deformation pattern, and it can be scaled to some real deformations. The number of mode is typically equal to the number of degrees of freedom in a structure. So in a tall building model like that you're making, what do you think, how many degrees of freedom will there be? Well, not infinity in your model. In reality, infinity, but in your model, how many? Guess. How many? Guess.
Depend on node.
I know, but just guess.
Oh, guess.
Guess, yes. For your 40-story building, how many? Easily 500,000 or 1,000,000 degrees of freedom in your model will be there, right? So we are talking about 1,000,000 natural frequencies of a model that you are going to create easily. But not all of them are interesting. Not all of the natural periods are interesting or even possible, right? Some are of such high frequency and the stiffness is so large that it will be very difficult to excite them. So not all natural modes can be excited. Only few can be excited. And those are called the significant natural modes. And we are always trying to find the significant natural modes of a structure. We should know how to extract modes, how to look for modes, what frequency range are we looking for, what modes are we looking for, how many, where. This is the most important understanding of structure. If you don't know how to do that, you cannot be a good structural engineer. I'm sorry to say that, but you can write it down and put it in your pocket. So if you want to be a good structural engineer, you need to be able to understand dynamics. You need to be able to understand modal response. You need to be able to understand how many modes are important, where to look for, how to get them, and all that stuff. For example, if you're looking for a tall building and you are interested in wind, you have to look for certain modes and certain frequencies. If you're looking for earthquake, you have to look for certain modes and certain frequencies. If you're looking for people walking on the slab, you have to look for certain modes and certain frequencies. All three could be different. So for all three different purposes, you may be looking at different modal properties. Not same modes will give you the three important information. And that is where understanding of the modal response is critical. For example, if you're looking at the modes for walking on the slab or dancing on the slab or jumping on the slab, you need to look at the local modes of that slab in that range of frequency that we are interested in. For earthquake, we want modes, maybe first 30 modes with mass participation, right? For wind, we may be interested in first 3 modes or 6 modes, right? Depends on what we are looking for. So we must know what we are looking for and what modes are relevant to that. You cannot look for all the modes. It's pointless, right? 500,000 modes is useless. Modal analysis should be done before applying any load. So when you do your project, you finish your model, the first thing I'd like you to do. Okay, first of all, let's stop here. You all have your model already?
Yes.
Correct. You all have ETABS viewer installed app?
Yes.
Yes? Okay. As soon as you finish your group finishes the model is complete, ETABS model is complete, please share it with me. You know how to share, right? Yeah. Go to the app, upload the model to your cloud, and then open the app in your phone or wherever, and then share the model with me. So I can see your model immediately, each group. Make sure that your model has a group number in the model and version, right? So group A, version 1, group A, B, group version 1, version 2. Every time you send me a model, revised model, change the version number and same group number so I can keep track of what you're doing. So I will be able to see your models on my phone wherever I am, and then look at the mode shapes and look at and then I can tell you I can see what you're doing, right? And then when you run the load cases, I can also see the results. So it will be very good for me to keep track of what you're doing all the time. So let's say from now on, every week on Friday, every group should send me their model state wherever you are. So currently, what is the state of your model? Preliminary sizing already done? Yes? Group leaders, please raise hands. Okay, 1, 2, 3, 4. 2 group leaders are missing. Okay, 5. 1 group leader is missing. Okay, please note that every Friday I must get, or every alternate Friday, whichever you want, I must get a model shared by you from your group so I can see the progress on the work. And that is how I'm going to grade your models. Previous class did not have this opportunity to share the model with me, but now we have the opportunity to. So I can see your model, and I like to comment on the model and send you back immediately, this is wrong. So I can check your models very easily and quickly, anytime. So send me first models. When can you send me? Next Friday?
Yes.
Okay, next Friday. Next Friday, send me the first version of your model, wherever it is. Doesn't matter, because so I can see what you're doing. So the first thing you should look at is the natural periods and mode shapes, and try to understand them. Okay. At least you should look at 12 modes, first 12 modes minimum for a tall building. So this model analysis should be done even before you apply dead load or anything, because it will tell you whether your model is correct or not. So application of model analysis, I'm going to leave this for you to read. Please read these slides when you get them. And they're also in my other talk on the blog and also on LinkedIn. I've written a lot about these things. Please read, find and read material about this one. There is on LinkedIn, if you are on the LinkedIn, you can find also a very good discussion about the importance of modal analysis and what you can get out of that. So please read that. So I leave that to you for read. This is an example of the modal analysis, and you can see from here that when you look at the modes, you can see whether the structure is symmetrical or unsymmetrical, because if it is unsymmetrical, you will see torsion in the building right in the first or second mode. If it is symmetrical, the torsion should be third mode, and first two modes should be just swaying in one weak direction, then second weak direction, then torsion. That's how a typical symmetrical building should look like. But sometimes completely symmetrical buildings have the first mode as torsion, and which surprises the engineers and shocks some engineers. How can it be? Because according to what is normally written about modal analysis, if the structure is symmetrical, then the first mode should be translation, second mode should be translation, third should be torsion. But if the structure is completely symmetrical, sometimes in tall buildings especially, you get first mode as torsion. Can anyone tell me when that can happen and why?
Stiffness.
Sorry? Stiffness, yes, but can somebody think of thing? This is really a good question for you to think. If you can come up with an answer, I will get you chocolates, promised, yes, like next time. Anyone? In what case can you get a symmetrical tall building to have torsion in first mode? I should ask that in the final exam.
Maybe a mistake during modeling.
No mistake. Perfectly no mistake. No.
Change of eccentricity.
No.
CG.
No, I'm saying perfectly symmetrical. You people are not listening. I'm saying perfectly symmetrical building, no change in CG, no problem with the eccentricity, zero problem with the, it's perfectly symmetrical building, but still has first mode as torsion.
Loading action.
Modal action is independent of loading, for God's sake, man. I just explained to you, modal response has nothing to do with the loading, it's a natural response. Do not talk about loading. If you talk about loading and modal together, some major misunderstanding. Cannot be.
Relative stiffness of beam column.
You are trying to go in the right direction, but not there yet. One more step. Maybe half piece of chocolate. Okay, I will come back to it in a minute. Think about it if you can find it. Otherwise, I will show you.
I think it's stiffness like beam column.
Yeah, but not really. I mean, like I said, maybe 20%. Correct. Okay, this is the modal analysis. This is how you should look at your modes. When you make the report for your project, I expect every group to have this kind of figure in their report and in the presentation, which should show this is the 9 modes of the building. But they are arranged in a certain pattern, which is very important to understand how we arrange them and how we look at them. So this way and this way, we are looking at different things. So it's not randomly arranged. These are the first 9 modes. But in this way, you can see T1, T6, T9, T1, T2, T3. So there's a certain order to this one, right? And there's a certain change in the natural period. T1, 5 seconds, T6, 1.28 seconds, T9, 0.7 seconds. But all of them are modes in only one direction. First, second, and third mode in that direction. First, second, and third mode in the other direction. First, second, and third torsional modes. And this is the natural frequency in this direction. First, second, third mode. But the program will give you modes like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. But you are not going to look at them in that way. You need to understand the directions and separate them into modes in particular direction, in particular order. Right? So, yes,
The ordering is not clear.
not clear. That's good. I don't want to make it clear. I want you to think about it. I just take this picture and think how you're going to arrange that. Please do some work at your end, right? Okay. I'm giving you a sample. I want you to come up with this. That is the project. If I explain, then what's the point? So get something like this. But remember, this one, this one, this one, this one. So we have already high mode effects. Do I have a video?
Touch again.
Hmm? This I've shown you already, right? Yes, no?
Not
Yeah,
this.
similar, but this not yet.
Video.
Sorry?
Similar, but not this.
Not this one. Okay, this video is showing you actually we made this video as a fun. It's also available on the internet. Originally, we thought we will get some performers to perform a dance based on these moves, but then we dropped the idea. So we just make a video. But please look at the videos, the mode shapes of the tall building and the direction. So this is which mode is this? First. Okay. Okay. Third. Exactly. So you should see and immediately know what mode is that from the shape, right? So this is the first three modes in weak direction. So you can see how the other direction, first mode, other direction, second mode, other direction, third mode. Really nice looking dancing buildings. So by looking at these mode shapes, you should be able to understand a lot of that. And for tall buildings, these higher modes, which are here and here, are very important. For short buildings, first modes are very important. But for tall buildings, we must be aware that the higher modes means second and third and more, sometimes even higher fourth and fifth modes in each direction are important. But actually, what I'm showing you is 9 modes. First 3 modes in each direction. So 3 directions means 9 modes. So minimum 9 or 12 modes should be looked at in a tall building. And this is the effect of those modes. This is a little bit advanced thing, but I think now you are ready to receive some advanced information. Especially related to earthquake and wind, because we're talking about lateral load analysis. So the understanding that the tall building response to these loading is dependent on the mode is very important. And this is a knowledge that 90% engineers lack. As I told you in Cebu, when I asked this question to professional engineers doing design for many years, they also did not have an understanding of the effect of the modes on the response, because nobody teaches this stuff in undergraduate. This is forget about the red and different colors. I will talk about that later. That's another question that I don't want to talk about right now. Just look at the blue line for now. Don't look at the other lines. It will confuse you. Blue line, this is the bending moment pattern from the first mode. This is the bending moment pattern from the second mode. And this is the bending moment pattern from the third and the fourth mode. So you can see that the bending moment developed in the various floors along the height varies a lot depending upon which mode is predominant. So if it's only one mode, first mode, typical bending moment which starts from the top and maximum at the point, at the base. That is how we think the buildings should have the moment. Zero moment at the top and maximum at the base. That's what we think. But actually in second mode, the maximum moment occurs at 20th floor, not at the base, right? And another mode, it may occur at 30th floor and 10th floor and then so on. And here in 35th mode, 34th, 35th floor. So the higher modes produce response in buildings at different locations. Higher the building, higher the effect of the higher modes. For a building very small, 5-10 story, this may not be important. But for taller building, the response contributed by higher modes is very important. So for now, just remember that. But if you look at the numbers, actually this is not such a big number, because This is 10 raised to power 9. This is 10 raised to power 8. So actually it is small. So even though the figure looks big, but the actual number is quite small. For moment, the effects of the higher mode is not that significant because higher mode moment is small compared to first mode moment, even though the pattern is different, right? But not so in shear. This is the shear generated by earthquake from different modes. Again, you can see the pattern of the shear is like this, not like this. It becomes nearly flat at the bottom, even for first mode. Higher mode shear is like this, but the scale is the same, 2 raised to power 7. So this means this number which is here and this number which is here, they are of the same scale. In fact, second mode and here, if you this is the shear, 30th floor, higher mode shear will be larger than first mode shear in real numbers also. So the shear is more heavily affected by higher modes than bending moment. This is a very important lesson for tall buildings, especially for earthquakes. So for earthquakes, the higher modes produce a lot of shear in the building, which is comparable to first mode shear. And for bending moment, first mode moment is larger, even though higher modes moment is generated at different location, but it may not change the results so much. But it may change in some locations. So this is a very important observation related to lateral response and modes. Wind is predominantly first mode behavior. An earthquake moment is first mode, shear is higher mode. So when you combine wind and earthquake, or when you want to design for wind and earthquake, it becomes pretty complicated, because then you cannot simply compare wind and earthquake unless you know the modal contributions from higher modes also in the two, right? So this creates start of the problems between these two forces, earthquake and wind. So in general, when we design building, in many cases, the bending moment is governed by wind, shear is governed by earthquake. And the reason is higher modes for wind do not help, do not add. Wind is almost first mode, all of it, shear and moment both. Earthquake, shear is coming from first mode as well as higher modes. So the earthquake response is governed by higher modes. So even though earthquake may be small compared to wind in first mode, but it will be higher than wind in higher modes, so total response may be higher. So this is an important observation that you should remember. It will affect many things later when we talk about performance-based design. Then I will talk about these different colors. Another important thing to remember is, you know the response spectrum curve already, right? Okay, so response spectrum curve, shape of the response spectrum curve and the natural response are very important, very critical, and higher modes are very critical. Please spend some time on looking at this shape. This is the response spectrum curve from Philippines. This is the response spectrum curve from Bangkok. Two different cities, plotted on the same scale. So what do you see here? Very different shape. For Manila, the response of the buildings which are of small visual period is very large compared to Bangkok. And in this range, the Bangkok spectrum goes up and then goes down here, whereas the Manila spectrum simply goes down like that. So you might be thinking, what's the big deal? It's a big deal. It's a big deal because for this Bangkok, the peak of the response is at 2 seconds, roughly. For Manila, the peak of the response is at 0.1 second, right? And at 2 seconds, if you look at 2 seconds, this response is about 25%, it's only about 1/3 or 25% of the response at 0.1 second. In Bangkok case, the response at 2 seconds is actually nearly 50% more than response at 0.1 second. So why is this information important for us? I'm asking you, you're all looking at me. It is important for us because the earthquake forces are generated from this number, which is the acceleration component, right? Force F is equal to ma, I told you. So that is the acceleration on that side, correct? So force will be generated based on that acceleration produced for that natural period. So what this graph, the response spectrum is saying is that if your natural period is 0.1 second here, and you are in Manila, you will get acceleration equal to 1g. So your lateral force will be equal to your dead weight. So if your lateral force is 10, your gravity load is mass is 10 ton, horizontal force due to earthquake will also be 10 ton. That's what the response spectrum is saying, right? But when the building, same building is 30 stories or 50 stories here, then it is saying that the response will be 0.15 G. So same earthquake or same, if the building is 40-story, the lateral load will be equal to only 10% of the gravity. But if the building is 1 story, the lateral load will be equal to full gravity, G. So that's how the response spectrum tells us how much force will be generated in a building of different natural periods. So if the building is small, natural period will be, it will be very stiff, natural period will be, okay, you haven't thought about it. 10-story building, what is the natural period of one 10-story building expected to be, roughly? 1 second, good. 1-story building, 0.1 second. So you know that, right? So that means if the building is just 1 story, natural period will be 0.1 second. So you expect a large force to be generated in that building, right? If the same building is 5 second, 50 story, roughly, then you will get only 10% force on that one. But higher modes, same building, 50-story building, first mode is here, but second mode is here, third mode is here. So as the mode become higher, they attract more force because of the response spectrum is going up and the period is becoming smaller. So same building, if you go back to my diagram, that's why I asked you to study this. This is the first mode, natural period 5 second. Second mode, in that direction, natural period 1.28 second. So this and third mode, 0.7 second. So if you plot this on that curve, you get this first, second, third mode of the building in that direction. So third mode has gone to now this one. So third mode will contribute a lot of shear because it is on the high end of the spectrum. And higher modes and more, another fourth mode will be here. The only difference is that less mass participates in those modes. More mass will be participating here. Because when the entire building sways this way, almost the entire building mass or 60% of the mass is passed. So mass and acceleration give you force. Here the mass participation will be large, even though acceleration is small, so you get a lot of force. Here the mass participation will reduce, but acceleration coefficient will increase, so you still get a lot of force. So which gives us very important two things. We have to look at the mass participation in each mode and also the natural period of that mode and look at the response spectrum. Then we will understand what will be the total response of a tall building to earthquake, for example, right? So this understanding is critical. Then you can design the building to your wishes. You want to reduce the earthquake force, you know what to do. Increase the natural period, move it away from the peak, right? So you go down on the spectrum. Or you reduce the mass, right? Or you reduce the mass participation ratio of that particular mode. So there's so many things that you can do if you understand this mechanism. You can design your building, you can fine-tune your building to reduce the dynamic force from the elastic spectrum. Second is that you can reduce the dynamic force by nonlinear response, which we will talk later. I'm just talking about the elastic response. Linear response can be reduced by optimizing the modal response of the building and looking at the response spectrum. So here in Bangkok case, we need to stay away from 2 seconds. So if the building has a natural period close to 2 seconds, it will attract the highest force, 20-story building, right? So either we have to be lower than higher, right? So that is quite an interesting observation for Bangkok people, that they don't want to have a building. So if somebody client comes to you and say, I want to make a 20-story building, no, please make 30-story, because I will give you smaller force, because 3 seconds will drop by half or less than half, right? So you can say, actually it will be more economical for you to design a 30-story building than a 20-story building. Not really true, but okay. So sometimes what we do is that if the building response is 2 seconds, we try to reduce the stiffness, make it soft. So if there's a big shear wall, we say, no, please make the shear wall smaller. We don't want a big shear wall, because big shear wall, more stiffness, smaller period. So in many projects, we have actually done it. We have actually asked the client to reduce the size of the shear wall or break the shear wall down into pieces so that we can increase the natural period and move it away from the peak, and it reduced the forces. So it is quite interesting that you can look at the response spectrum, you can look at the modal response, and you can design the building to reduce less forces, right? Any questions on this? Everybody clear? You might get a question of this kind somewhere. So 25-story building, different mechanism. So this is the story of a 50-story building. Same building, every 25-story, then you can see that 80% mass part is coming from first floor. If in this one, and here 15%, 4%. So it will depend on that. So the 80% mass multiplied by this, very large force, right? In this case, 50% mass multiplied by that small force, 30% mass by very high acceleration, and 10% mass multiplied by that. This is the mass participation ratio. So looking at the natural period, looking at the mass participating in that mode, and looking at the response spectrum curve, you can understand a lot and improve the lateral response of the buildings. The natural period also is affected by other things. So natural period is of course affected by mass, structure, attachment, occupants, stiffness of the tower, podium, basement, foundation, and soil. So this is the structure. The total natural response will depend on the stiffness of the tower, stiffness of the podium, stiffness of the foundation, stiffness of the soil. So you can play with these things to get what you want from the building. So as a designer, we have a lot of innovation that we can do. You don't have to just accept the project that you get and just design it as it is. You actually have a lot of things that you can propose, you can study, you can refine to improve the design. That's what makes one designer better than the other, right? Because they understand something more than the others, and they are able to bring that to the design. So you already know stiffness is affected by material, cross-section, member, foundation modeling. So you can spend some time on improving that. So as one exercise that I want you to do when you finish the model is to change the natural period of the building, of the same building, to get the minimum base shear based on what I've just explained to you. So one part of your project's outcome should be that what will I do, what will I change in the building so that I get the least base shear for that building by modifying the natural periods, by doing something, by looking at the response spectrum of your project and giving me, let's say you tried 3 different things, then you can say if I change this one, I will get this natural period, this mass participation, this total force. So when you do that, please note down, I want this to be in the report, least base shear refining the structure for least base shear from earthquake. Okay. So another thing that we can do is cracking factors, which are given by the code. You assume certain amount of cracking to exist in a structure, and that also changes the stiffness, because we do not expect the structure to be perfectly cross section. We expect it to be cracked at some point in life. So you normally estimate the response of the structure at different levels of cracking. There are cracking factors in the code that you will apply to your model. So once you do not apply any cracking, you will get a certain natural period and certain base shear. And if you apply cracking, you will get a different base natural period and a different base shear. So then those two are also your extremes. Actual will be in between somewhere. So over the life of the time or life of the structure, natural period keeps changing because it keeps cracking. The structure gets damaged. So natural period is not constant property over the life of the structure. Skip this a bit advanced to advanced. So coming back now to the big picture for earthquake response from this whole thing that we talked about. When I will talk later, let me today talk about earthquake, lateral response of earthquake. So this is the main equation I've shown you, and this is called the nonlinear dynamic equilibrium equation of structures. So all kinds of response are governed by this equation. There is no structural response that is outside of this equation. Okay? If you can find one, please do let me know that you think it's not covered by this equation. Anything comes to your mind? Think of something, some response that you think is really weird, and we will see whether it is part of this equation or not. Think of any strange response of a structure that you never thought about, and let's see if we can fit it here or not. I need 3 weird responses. I give you example. For example, traffic on a bridge, or ship hitting a structure. Anything. Think of anything that you can imagine that structure might be subjected to, and we will see whether we can handle it by this equation or not.
Temperature.
Okay, temperature. Good. Temperature is a change in, what is the temperature?
Because of expansion and contraction of the member.
Right.
And because of that force is exerted, compression tension.
Correct. Right. So that will be part of the force. We can convert that into, but you are right. She is right in a way that directly what we need to do in that case is we need to apply this U as a given number rather than calculating. Normally what happens is that for this particular case, the way that we will use this equation is, normally we know the force and we calculate displacement, right? In your case, the displacement is known as the expansion from the temperature. So we put that known displacement into this one and find the force required to restrain that with a certain stiffness.
Temperature is also non-linear, right?
Temperature is not nonlinear.
And non-linear.
Temperature is linear. Normally the response to temperature is linear. Temperature may change in a different way, but normally when we do the structural analysis for temperature, it's a good question actually, very good. She's picked a good example. Because when you do the temperature, we normally what we say is that I would like to see the response of the structure when the temperature is, so it's a natural temperature, and then there is a temperature increase, delta T. So it doesn't matter what is the real temperature. It's the delta T that we are worried about. So normally when we do the temperature analysis of buildings or structures, we normally specify a delta T. Change of temperature from one time to another time. Let's say summer and winter. So we would like to see what forces will be generated in this structure, or what deformation will happen in this structure if we change the temperature of the structure by 20 degrees or 30 degrees over the year. Or You can say what happens in one day, night and day. Morning is 40, evening is 20 degree temperature change. What will happen to the structure? It's a good question, and we have to do this. You can also say what will happen to the structure if the top of the slab is hot and underneath the slab is not hot, is exposed, right? So the top temperature is 40, below temperature is 30, 10 degree temperature gradient in a structural member. So these are the type of temperature problems that we normally solve in a structure. But they again come back to the same equation because we specify the displacement because we know thermal coefficient. So we multiply the thermal coefficient with the temperature gradient delta T. We get the strain total expansion, and then we put that expansion here, and based on the stiffness we can calculate the forces generated in the structure. You understand my point? Yeah. So yes, similar questions for creep, shrinkage, and temperature. All these are handled in the same way. They're handled by assigning a strain change or a displacement change in the structure, and then calculate the forces based on the stiffness, rather than applying the forces and calculating displacement. So here the displacement is known in the members, expansion is known. Good. Any other example? One more. Any other behavior that you think might not be covered here? Flooding is a force, right? So we can calculate, we can relate with time. So almost every machine vibrating on the floor is a dynamic force. So almost everything that you can imagine that can happen to a structure can be determined by this good equation, right? So this, for earthquake, we can simplify this equation in many ways. For example, if you remove these parts, this, and this, you think the structure is linear, elastic, and static, we can use equivalent static force, which is used by the codes. They give you equivalent force that is coming from this part of the equation. If you say, I would like to do a pushover analysis, we take some part. If you say free vibration, you take some part. Response spectrum, some part. Linear time history, some part. Non-linear time history, some. So all type of analysis for earthquake are done by the same equation. We just consider some part and ignore some part. But ultimately, what we want to do is we want to use the full equation. That's what is performance-based design. That's what we do. That's what AIT is good in doing performance-based design, using the full nonlinear equation to solve the response, including all kinds of nonlinearity and all kinds of dynamics in there. Construction stage analysis, dead load increase, whatever you can think about, stability, P delta effect, everything is included in the analysis. That's the complete thing that we want to do. So other analysis, P delta, buckling, static pushover, fast nonlinear, large displacement, they're all coming from the same, they all come from the same equation. Free vibration, response spectrum, steady state. So you can do even wind dynamic analysis can be done by the same equation, because we apply a force changing with time to the same equation, measured from wind tunnel or somewhere. So almost every kind of analysis can be done. I can assure you, inside SAP and ETABS, they're just solving this equation in different ways. That's all. So analysis procedure, these are the 4 analysis procedure specified in codes and in documents that you need to do for your project normally and for your buildings. First one is linear static procedure called equivalent static analysis. So the building codes just do that. If you follow the building code formula, they will just give you, number one, the lowest level of analysis with the most approximate and inaccurate results, especially for tall buildings. Not suitable for tall buildings. So we never do that. Cross. We don't do that. If you want to do that, don't come to this class. Second one No, we still do that for some reason. Non-linear static pushover analysis. This is not dynamic but non-linear. It is still static but non-linear. That means we take the equation and we do not take the mass and acceleration and damping, but we take the non-linearity part. This is very useful analysis for buildings if we want to determine their capacity or pushover curve. And this was very popular at one time. It still is popular for short buildings. Not so good for tall buildings. We still do it because it has good knowledge, good information there, and we should try to understand how it works, and we can still do that. So this is quite interesting. Non-linear static pushover, when we used to teach this a lot in seminars, I used to do so many seminars on pushover analysis in 10 years ago. We don't do that much now. We should do that, but we don't do that much. Then linear dynamic procedures, response spectrum analysis and linear response history analysis. Response spectrum analysis is the most common analysis method that people use when they run ETABS or other programs. But the people who developed this method, I met him last time when I was in US. He's now 90-year-old. It's 1992, but he's still very active. And now he writes so much against this method that he proposed, and he said, I regret that I proposed this method at that time because it is not good, and he finds so many faults in it. But at that time when he proposed, there was no other option. So this has been the most popular method of analysis so far for earthquakes, response spectrum analysis, where you have a response spectrum and what I showed you just now. But Professor Wilson, who proposed this method, now is very against it. And he was telling me, you must stop using that. And we already listened to his advice. We are not using it much now. We try to use linear response spectrum. Instead of that, we use linear response history analysis. And most of the time, we are using nonlinear dynamic procedures, the last one. The most sophisticated one, so far the best one, or as we say, the most accurate one. So if you use this analysis, this is the best one so far. But it's difficult, time consuming. But most of you, when you do thesis, if you do thesis on analysis side, you will be using this one, right? But this is only used for small buildings. Sometimes this is response spectrum is still used a lot. We still use pushover analysis. In fact, the building that I showed you, the video, is taken from pushover analysis. That is a linear static pushover analysis that gave you that nonlinear curve. So it is a good method. But ultimately, this is the one. Professor Penning is not in favor of this so much. Not that he knows this is the best method. The problem is that engineers are not familiar. You need too much data, and people can make mistakes. So instead of this, he's thinking to improve this method, and they're working on that to make this. Make this response spectrum analysis better and remove some of the problems that we have in that method, rather than completely remove that method, which is a good approach. So a lot of our students, your seniors, have done PhDs and master's theses on improving this method to match with this method somehow, right? So it's a good research also if you want to work on that area. So nonlinear dynamic time history analysis, this is the benefits and the disadvantages. So I'm going to stop here for any questions. So first of all, the advantages are this can be applied to all kinds of structures. The advantages are you can handle all types of loading. Advantage are you can handle non-linearity, you can handle damage, you can handle everything. Disadvantages is complex, needs more information, needs tools, needs skills. It takes about, in our experience, it takes about 1 or 2 years for people to learn this method to apply correctly. So if you invest about 2 years in this one, then you will be able to use this method. Response spectrum, this can be sensitive to changes in many things, so you need a lot of understanding, right? So I leave this to thesis later. Okay, let's stop here. Any questions about what we talked today? So what did you get? This is an important lecture, so let's have a quick review of what we understood today, because this is, to me, an important discussion of the lateral response of tall buildings. Start with you. What did you learn?
So important thing is like shear is dominating in the higher mode and bending is dominating in lower mode. So we have to consider this within earthquake and wind.
Excellent, very good. Do not forget that. Okay.
About the influence of the wind and earthquake effect to the shape that graph you show maximum in the base.
Yes, yes. So that, please remember that graph. It's an important graph. Yes. I showed this slide in the Vertical Cities conference also, and a lot of people, very experienced engineers, we had a lot of discussion about that. Yes.
Only significant number of mode are useful in model analysis.
Good.
The other thing is that for model analysis, we always have to look for time period and mode shapes. Should always be considered.
Okay.
Response pickup and how we invoke the structure, looking for mass specific and
Good. Okay. Very good. Yeah.
Bending moment, they are governed by wind, and shear, they are governed by output. But for first mode, it's like wind govern the bending moment and output govern shear mode. But for
Okay, you got something, but I think this is important. But please remember, there's a lot of other things in the lecture also. Don't forget that about the importance of the natural period, and finding the significant. Okay, next one.
for the same acceleration, begins with different time periods.
Correct. Very important thing. Excellent.
Data analysis for mass participation and response at spectrum analysis, and this will also the critical to improve the lateral response of the building.
Nice.
The first mode moment of for the earthquake thing, the first mode of moment, that contribute much about model analysis. But I still wonder about how higher mode of shear contribute. I mean, we have to consider a lot of model analysis with shear.
Yes, normally that's a good question. And normally when you do the analysis, you must select several modes to be included in the analysis. So program will sum up, get the results from many modes, and then combine the modes by using some. We cannot add them together because those modes do not occur at the same time. So we normally combine them using different modal combination rules. For example, SRSS or CQC, something like that. So those combination of modes is important. That's where we combine them. But the problem is when you combine them, you lose the individual contribution because we combine them using some arbitrary combination rules. That's why it is important to look at each mode separately also.
and learning about the model analysis is very important for us to understand the behavior of the building, and we have plenty of modes, but we should focus with the significant.
Very good. Next one.
To reduce the earthquake force, we need to reduce the natural period, and then
Reduce or increase?
increase. And then you mentioned about the unsymmetrical and symmetrical structure, that torsion will be in the third mode for symmetrical, right?
Yeah.
But you didn't. You asked us like what was the case that symmetrical structure can have torsion in first mode.
Okay.
You didn't answer that.
I did not answer that. I know I didn't answer that because I want to keep something with me, some secret with me. Okay, the case is core buildings. When you have a building which has a central core and completely symmetrical, the core has all the stiffness, but outside there is no stiffness. So the building starts to rotate about the core because core is the center. So there is no torsional stiffness of the building. So before it can bend, it starts to rotate. So that means if you have a weak frame on the outside and if you have no walls on the periphery, then the building will start to rotate. So a building which has a core wall and flat slab structure will have the first mode as torsion, unless you put some frames on the edge. That means it's weak in torsion because it has no torsional stiffness. Now you got the answer. Okay. Next one.
I learned that benchmark spectrum is very important for the
higher than the other mode. Just happen in the different location of the building.
Yeah.
Second one is shear normally happen in the higher mode comparing to the first one.
No, it happens in all, but shear is relatively, contribution is higher in the higher modes as well.
Not only the highest building can be dangerous, but also short building depend on the natural periods.
Yes,
That's
and
down to responsibility.
Yes, that's true. In fact, short buildings can be more critical. Typically, short building in general get more percentage of the force than the tall building. For a short building, the percentage of the force that is generated for horizontal may be as high as 25%, 30%, 40%. For tall buildings, we normally get 5%, 7%, 8%. So tall buildings, actually the total force generated on tall building as a percentage of the weight is always smaller than the short building as a percentage of the weight. So that way, tall buildings are less dangerous in earthquake than short building. But people always think, oh, earthquake and tall building. Actually, it's the other way around. It's a short building which you should be worried about.
I learned that different modes are significant for different types. Like for wind, different modes, for earthquake, different.
Correct.
For load in the slab.
Yes, very good.
Looking at the response spectrum, we try to avoid the maximum response by changing the natural period. To do that, we can either change the mass or stiffness, and we should also consider the mass participation factor for various modes.
Very complete, perfect. Okay.
Few things like first of all, I would like to focus on the changes of the mode shape due to the different loads. Like it still is the challenge to engineers to comprehend the wind and
Again, you are making the mistake that you should not make. You are relating the modes to the loads. Modes are not related to the loads.
Like due
So
to the wind effect and earthquake effect, the modes are coming different.
No. Again, we are not understanding. Modes are natural properties of the structure, but the wind and earthquake are forces and displacements, right? I showed you last time that earthquake is a displacement, wind is a force. That's why when they interact with the modes, they interact differently. But they don't generate the modes. Yeah. Please remember, forces do not generate modes. Modes are generated by the structure by itself. It's a property of the structure. And these modes interact with forces or displacement to generate response. And that's what we are looking at. So if you try to think about modes and forces together, you are making a big mistake.
Okay. And then to reduce the dynamic response, we can reduce the mass and increase the time period. And we can also reduce the stiffness.
Right. But not always. I showed you the example of Bangkok. In Bangkok, actually, by reducing the natural period away from 2, you can also reduce the response. Not always. It just depends on the response spectrum, right? So you have to look at that, where you want to be. Yes,
Okay,
please.
I've learned that to analyze the response of the building to horizontal movement,
Yes.
it depends on many factors like the mass participating
Mhm.
of each mode,
Right.
and also the acceleration spectrum, which is suggested to be stay away from the peak
Correct.
acceleration.
Correct.
Okay, and I learned that like a traditional nonlinear static analysis is still used in short building.
Yes.
Yeah, and some kind of other like linear dynamics procedure that we try to develop response spectrum analysis to be equivalent to the what is that? Nonlinear dynamic procedure.
Excellent. Very good. Very good summary. Don't bring your phone to the exam.
I take note in my phone.
Okay. Okay, good. Very good. Okay, I think that's good. So we will meet next 3 weeks. I'm not traveling, so we will try to finish our course in the next few lectures. Okay. But please, next Friday, do not forget to send me your models, upload your models, and so I can continuously monitor your progress on the project. Okay. Thank you.